Welcome back to GISC 1336. Today's lecture is going to cover construction surveying. We're going to be talking about bridging the gap between efficiency and accuracy. And as we move forward from the concepts we explored in site surveying, we're going to be stepping into what is often called construction surveying. So we'll go through an introduction. We'll talk about surveying in the AEC industry, surveyors' role across project phases, construction layout, profiles and vertical curves, technology integration, QA/QC, liability, and board standards as always. And then we'll talk about the skill set that bridges between engineers, surveyors, and the broader professional. And then we'll take a look forward into what comes next and wrap everything up with a conclusion. This is where the work of the surveyor intersects directly with the built environment. We've talked about how boundary surveys define ownership and how site surveys capture existing conditions. Construction surveying takes the next step. It translates design into the physical world by providing the control, layout, and verification needed to build projects safely, accurately, and most importantly, according to plan. As surveyors and drafters, we must understand that construction staking and layout are not just about putting points in the ground or drawing alignments in Civil 3D. They're about communicating the design intent in a way that is both precise and reliable. If the site survey is the foundation of design, then the construction survey is the framework that allows that design to rise out of the ground. At the same time, we should acknowledge the growing role of GIS, or Geographic Information Systems, in the construction process. GIS operates at a different scale than a construction survey. And while the surveyor is concerned with centimeter level accuracy on a specific site, GIS provides the broader geographic context, zoning boundaries, floodplains, utility networks, transportation corridors, and environmental constraints. Increasingly, survey data is not only used to guide construction, but it is also integrated into GIS databases for long-term management. This means that the work we produce in Civil 3D may eventually inform not just a contractor on the ground, but a city planner, a utility manager, or emergency response team years in the future. In Texas, this overlap has a real potential for consequence. The board rules emphasize that licensed surveyors are responsible for ensuring layouts reflect both the approved design and the legal boundaries. But once those deliverables are digitized and shared, they often flow into GIS systems maintained by municipalities and state agencies. And that means the surveyor's precision feeds directly into the geospatial record of the state. A misplaced stake might affect a construction project today, but a mislabeled deliverable could affect GIS data relied on for infrastructure planning decades into the future. And this is why it's important to view construction surveying as part of the continuum that includes both traditional surveying and geospatial data management. In Lecture 5, we'd looked at boundary law and the hierarchy of evidence, which ensures that ownership is clearly defined. In Lecture 6, we explored site surveys, where topography, drainage, utilities, and vegetation are captured to support design. Now, in Lecture 7, we're carrying those principles forward into the field, where alignments and profiles in Civil 3D connect directly to stakes, marks, and as-built conditions, while also recognizing how that data may later live within a geospatial framework. So in this lecture, we're going to talk about the role of the surveyor in construction, how survey data ties into the architecture, engineering, and construction, or AEC industry, the technical tools in Civil 3D that support layout and verification, and the ethical and professional duties that guide every step of this process. Along the way, we'll also reflect on the ways that GIS and surveying complement one another, ensuring that what we build today remains useful and accurate in the digital records of tomorrow. When we talk about construction surveying, we cannot look at it in isolation. Surveying is part of the larger AEC industry. Each of these disciplines brings its own perspective, but surveying still provides the backbone. Without survey data, architects have no accurate canvas, engineers have no reliable model, and contractors have no instructions for where to build. Surveying is the skeleton of control upon which the entire project rests. And surveyors play a role at multiple stages of the AEC process. During pre-construction, survey data defines the property lines, topography, utilities, and drainage that will set the stage for our design. In the design phase, site survey data is used to generate plans, models, and permits. And during construction, surveyors lay out the design on the ground, staking alignments, profiles, and benchmarks that all transform digital drawings into physical reality. And then finally, in the post-construction phase, as-built surveys confirm that what was designed matches what was built, feeding back into the legal records, maintenance plans, and often, more in these days, into GIS systems or BIMs. This overlap with GIS is worth pausing on, because GIS operates on a broader scale than Civil 3D. And while Civil 3D is concerned with precise site-specific design, GIS ties those designs into the larger geographic framework: floodplain boundaries, zoning overlays, transportation corridors, and environmental data. Increasingly, survey data flows directly into GIS databases maintained by municipalities, counties, and state agencies. And in Texas, this means that your work as a surveyor may show up in a city infrastructure inventory, a county floodplain management system, or a TxDOT's transportation planning GIS. All reasons why ensuring you have high quality, high fidelity work is important as a professional, because you never know when someone may call you back. And so the surveyor's role then is not just technical, but integrative. You are the one ensuring that the data collected in the field, the points, the elevations, the alignments, the profiles, can be trusted not only by the engineer designing the road, but also by the city planner managing development 10 years down the road. This is why accuracy and clarity are paramount. If you mistake a line during construction, the building might be displaced. But if you miscode a deliverable that enters a GIS database, it may mislead decision makers across dozens of future projects. To put this into perspective, think back to Lecture 5 on boundary surveys. There, we emphasized the hierarchy of evidence and the surveyor's duty to preserve clarity in retracing property lines. In construction surveying, the principle is the same. Clarity and accuracy protect not only the current project, but the records that will be relied upon long into the future. The difference is scale. In boundaries, we're protecting ownership and rights. In construction surveying, we protect the integrity of the built environment and the geospatial records tied to it. So as we think about surveying in the AEC industry, remember this. Every survey is both local and global. Locally, it defines stakes, alignments, and profiles for a single project. But globally, it becomes part of the geospatial fabric that ties together infrastructure, utilities, and land use across the state. And this is why the overlap between Civil 3D and GIS is not a side note, but a central feature of modern surveying practice. And the role of the surveyor in construction is not confined to one moment in time. Instead, it stretches temporally across the entire project lifecycle, from pre-construction through design and construction, and into post-construction verification. At each of these stages, the surveyor's contributions are unique, but the principles remain the same: accuracy, clarity, and professional responsibility. Understanding when and where certain changes or decisions were made can be vital to understanding how where a project may have started ended up to what it is as its as-built condition. In the pre-construction phase, the surveyor provides the foundational data of any project. This includes boundary surveys to establish ownership, site surveys to document topography, vegetation, drainage, and utilities, and sometimes specialized surveys like floodplain, tree surveys, or airfield surveys. This is the stage we emphasized in Lecture 6, capturing existing conditions so that designers can build upon a reliable record. In Texas, these deliverables are often tied to the State Plane Coordinate System and the NAVD 88 datum, ensuring that the site can be tied into local and regional records. Increasingly, this data is not only handed to the design team, but is also ingested into GIS systems managed by municipalities or state agencies. And this means that pre-construction survey data may later inform our zoning maps, floodplain management, and infrastructure inventories. And the surveyor's accuracy here carries forward long after the project is complete. And you'll notice I'm repeating some of these phrases over and over again, seeing where your data is going to go. And in case you're an individual who already has some land surveying experience under your belt, you might think surveying, GIS, these are completely different fields. I want to do one or the other. Why do I need to know both? Well, take this. Look at your software. Whether you're in ArcGIS Pro, you're in Civil 3D or AutoCAD, you're going to start noticing there's a lot more overlap. There's a lot more tools to help import and export from one system to the other. It's becoming streamlined. It's becoming commonplace for this to be the role of us as drafters and us as GIS analysts. We're now working to bridge that gap even further as the people who create our technology to do our work are starting to cooperate with each other. Industry is demanding this, so be prepared. So during the design phase, survey data flows into tools like Civil 3D. Alignments and profiles, the focus of our practicums this week, become the framework for roadway design, utility placement, and grading. This is where survey deliverables evolve into design models. The drafter's role here is critical. Using the alignment creation tools or automated methods like from objects ensures that the surveyed path becomes a formal Civil 3D alignment. Profiles then translate surveyed elevations into ground sections along those alignments. And the accuracy of this translation determines whether the design remains true to the land surveyed in the field. From a geospatial perspective, this phase is where survey level precision is married to planning level context. Civil 3D gives us detail at that centimeter level, while the GIS often places the project within its regulatory and geographic framework. A good surveyor is going to ensure that both of these are consistent. And in the construction phase, the surveyor's work becomes most visible. This is where construction staking happens, and it's one of the most common things that we'll do during construction surveying, the staking. And that's transferring the alignments, profiles, and design data from Civil 3D back into the field. Stakes mark the center line of a road, the edge of pavement, the location of utilities, or the footprint of a building. This phase is where errors become most costly. A misstaked alignment could shift a road out of its right-of-way. An incorrectly profiled grade could cause drainage failure. This is why QA/QC, which we practiced in Lecture 6, is essential before deliverables leave the survey office. Every alignment, every profile, every label must be double-checked against the design intent and the field data. Otherwise, you'll end up with road construction projects like we see all the time across the state. Freshly resurfaced roads immediately has new potholes. Something wasn't done right. And it's our job to push as an industry and as professionals to ensure that in the future that changes. And GIS plays a quieter role here, but it is still present. In some Texas municipalities, inspectors rely on GIS-linked construction management systems, where survey data must align with official records. A construction stake is not just a physical mark here. It's part of a larger geospatial workflow. And then finally, in the post-construction phase, the surveyor performs an as-built survey. These confirm that what was designed is what was built, documenting the location, elevation, and dimensions of improvements. As-built surveys not only close out the construction project, but also update GIS systems, legal records, and future maintenance plans. In Texas, as-builts often become part of the city and county GIS databases. The drainage pipe you surveyed today may be part of that floodplain study 10 years from now. The roadway alignment you staked may become part of TxDOT's digital transportation records. And once again, surveyor accuracy has long-term implications. So the surveyor's role in construction stretches across 4 phases: pre-construction, design, construction, and post-construction. At each stage, the workflows between Civil 3D precision and GIS context, ensuring that the project is accurate today and remains useful in the records of tomorrow. And as we've emphasized in every lecture, every line you draw is either helping or hurting the surveyor's certification. So construction layout, in a little more detail, is the stage where survey data moves directly from the computer screen to the ground. This is the point where alignments and profiles created in Civil 3D are transferred into stakes, marks, and reference points that will guide contractors as they build. In many ways, construction layout is the ultimate test of survey accuracy. If the surveyor's line work in Civil 3D is even slightly off, the stakes set in the field will be misplaced. That means a roadway built outside of its right-of-way, utility installed at the wrong depth, or a structure constructed out of alignment. The consequences are not just expensive. They could involve regulatory violations or even threats to public safety. This is a highly visible portion of our profession as surveyors. So, it just goes to say that you need to make sure you're doing proper QA/QC. Everybody is watching. And you'll notice as we practiced in Lecture 6 lab, alignments in Civil 3D are the foundations of roadway design. They define the path the road or corridor will follow, including curves, tangents, and spirals. In the field, those alignments become stakes and offsets that contractors will have to follow to lay down pavement or utilities. Creating alignments in Civil 3D is not just a drafting exercise. It's the first step in ensuring the construction layout will succeed. Whether we generate them with the alignment creation tools from objects or as offsets, or co-going it out in the field, every alignment represents a decision about where something will be built. And once it is staked in the field, that decision will very soon become a part of physical reality. Now, profiles, which we've built in the practicum exercises for Lecture 7 represent the vertical dimension of design. A ground profile shows the existing terrain, while a design profile sets the intended grade. In construction surveying, those profiles translate into cut and fill stakes, grade checks, and elevation marks. And vertical curves are particularly important here. They smooth the transition between tangents in a profile, ensuring that roadway and utilities meet design standards for safety and performance. When surveyors stake these grades in the field, they are making sure the contractor builds the roadway or utility with the correct slope and vertical alignment. As we said in Lecture 3, contours are the language of the ground. In construction surveying, profiles and curves are the language of how design interacts with that ground. The drafter's precision in Civil 3D ensures that the survey crew's stakes match the engineer's design intent. No construction layout can succeed without reliable benchmarks and control points. Benchmarks are known elevations tied to a datum, often NAVD 88 in Texas. You'll learn more about datums in your future courses. Don't worry too much about those right now. And then our control points are horizontal references tied to state plane coordinate systems. Together, they form the skeleton of accuracy for every stake set on site. If benchmarks or control are misplaced, every downstream stake will be wrong. This ties back to Lecture 5's principle of retracing evidence. Just as a boundary surveyor must begin from a known, reliable monument, a construction surveyor must begin from verified benchmarks and control points. Only then can they align their alignments and profiles so they can be trusted in the field by the construction crews. And while construction layout may seem like a site-specific task, it too connects to GIS. Many municipalities in Texas now require as-built data, including alignments, profiles, and benchmarks. These must be submitted digitally for inclusion in both citywide GIS systems and engineering department records. And that means the stakes you set today may define the data layers that city planners and utility managers rely on for years to come. And before you start thinking, it's just more stuff that we have to provide to the city, think of it in a kind of a reverse perspective as well. You're starting a project in an already built out site. You need preliminary information in order to get your project started, to understand where you're going to be doing work. As municipalities continue to increase the value and the robustness of the information that they have on hand and publicly available, you now, as the project manager, as the surveyor, are going to be able to access this data so that you will have a head start in your projects. And you're not trying to rebuild everything from scratch every time there's a project. And I'm not just talking 10 years down the road. In a lot of our fast growth areas, I'm talking a couple months later. But if a different company is the one that did the previous project, and if that information didn't have to be submitted to the municipality, the likelihood of you getting your hands on that information, slim to none. And finally, remember that construction layout carries the same weight of professional responsibility as boundary or site surveys. Board rules make clear that surveyors must exercise care in all surveying tasks. A misstaked point is not just an error in construction. It's a reflection on the surveyor's seal. And that's why QA/QC, which has been emphasized in our Lecture 6 lab, and all of our lectures up to this point, is always the last step before any construction deliverable leaves your office. Looking at our Lab 7 exercise, we moved from creating alignments to building profiles and vertical curves. The purpose of this was to take the horizontal framework of a design and give it its vertical dimension. Alignments tell us where a project lies on the ground. Profiles and curves show us how it interacts with elevation, slope, and grade. The first step in this process was building a surface profile, and that profile represents existing ground conditions, sampled along with alignment. It is essentially a cross-section unrolled into a new line. It's a way of seeing the rise and fall of terrain along the path of a roadway, drainage ditch, or utility line. And on top of that surface profile, we introduced a design profile, which describes the intended grade the engineer or designer wants to impose. Together, these give us the comparison needed to plan cuts, fills, and grading. The introduction of vertical curves is where design becomes both functional and regulatory. A tangent in profile is simply a straight slope, but without curves to connect them, a road would be unsafe, unusable. Sometimes that's how they're built. Not saying it's right, it's just a fact. Now, vertical curves, they smooth our transition, and their parameters are not arbitrary. For example, crest curves must be long enough to provide stopping sight distance, while sag curves must accommodate proper drainage and driver comfort. These standards, they're not supposed to be optional. They're not optional. They're not always followed, but they're not optional. They are governed by engineering practice, and in some cases by state and municipal codes. The surveyor and drafter, therefore, carry the responsibility of ensuring that the design profile meets these requirements. From a surveying standpoint, accuracy in profiles is directly tied to field data and control. Every elevation sampled for the ground profile must tie to a reliable benchmark. Again, in Texas, it's typically NAVD 88. And if those benchmarks that we're using are off, the entire vertical picture will be distorted. Similarly, when a design profile is created, it must be checked against datum and tied to the same control framework. If it's not, the grade stakes set in the field will likely be wrong, leading to costly construction errors. And the profiles we develop in Civil 3D are not just drafting exercises. They are direct instructions for the field. A contractor uses grade stakes derived from these profiles to cut, fill, and pour. A misplaced curve on screen becomes an incorrectly graded road or an out of compliance drainage slope in reality. And this is why quality assurance and quality control are emphasized so strongly in our Texas surveying practice. Before any deliverable leaves the office, it must be checked for alignment, elevation, and clarity. Profiles also connect beyond construction into the world of GIS and long-term spatial data records. While vertical curves themselves are not typically stored in geospatial systems, the finished grades and as-built elevations often will be. Municipalities in Texas rely on these data sets for floodplain modeling, roadway maintenance, and infrastructure planning. So the accuracy that you establish in a Civil 3D design profile can influence decisions made years or even decades later, or as I stated earlier, maybe just a couple months down the road. In summary, profiles and vertical curves form the vertical backbone of construction surveying. They extend the work of the site surveys into the realm of buildable design, ensuring what exists on paper can be constructed safely, legally, and sustainably. And the precision of this work protects both the integrity of the project and the professional standing of the surveyor who certifies it, and not to mention the public at large. So, construction surveying today does not exist in isolation. It sits within a web of technologies that extend from the field to the office, and from the surveyor's control points all the way into the municipal GIS databases. And while Civil 3D provides the drafting and design environments for alignments, profiles, curves, and tools, It's the BIMs, GNSS systems, drones, and machine control. They're all increasingly part of the workflow. The challenge for the surveyor is not simply to learn each tool, but to ensure that all of them integrate seamlessly without compromising accuracy. So Civil 3D is often the bridge between raw survey data and a building information model, or a BIM. And BIMs represent the broader 3D model of a project, encompassing architecture, engineering, and construction details. Survey deliverables created in Civil 3D, your alignments, profiles, and corridors, often feed directly into BIM models. This makes the drafter's precision in Civil 3D not just a matter of internal accuracy, but a question of interoperability with the engineers and the architect's systems. There's a lot more we could say about BIMs here, but we can save that for a future specialized course. So in the field, GNSS, or Global Navigation Satellite Systems, have become the standard for setting control and staking. GNSS, or just GPS in general, allows surveyors to set points and collect elevations with higher precision over large areas. In Texas, where many projects span wide corridors, GPS provides efficiency that traditional total stations cannot match on their own. But GPS introduces its own risks: multipath errors, satellite availability, data mismatches. These can all degrade our accuracy. Under board rules, it's the surveyor's responsibility to account for these risks and verify that our GPS data um, is accurate when compared against our control benchmarks, and that we must certify that our deliverables are correct. Drones are another technology reshaping construction surveying. They allow surveyors to rapidly capture topographic data, site conditions, and progress monitoring. Drone-based photogrammetry creates point clouds and digital terrain models that can be imported into Civil 3D or other geospatial systems. And while drones provide efficiency, they must be carefully integrated with ground control to ensure that their outputs meet the same standards as conventional surveys. Again, the responsibility will fall on the surveyor to certify the accuracy and to ensure that photogrammetry does not replace, but rather complements traditional methods. And perhaps the most direct integration of technology into construction is machine control. Modern bulldozers, graders, and excavators can be and often are guided by 3D models uploaded directly into their onboard systems. This means the design profiles and alignments built in Civil 3D may be used by operators without surveyor intervention on every stake. And while this technology reduces field staking requirements, it does not eliminate the surveyor's role. The surveyors must ensure that the models uploaded into these machines are correct, tied to proper control, and verified against benchmarks. Any error here can translate directly into earthwork mistakes on a massive scale. And finally, as we noted earlier, survey data is increasingly tied into GIS systems at the municipal and state level. Alignments, profiles, and as-built conditions feed into citywide infrastructure databases. And these systems are used for long-term planning, asset management, and regulatory compliance. In Texas, TxDOT, county floodplain managers, and city public works departments all rely on GIS that incorporates survey-level data. And that means construction surveying is not just about the immediate build. It's about creating a geospatial record that will endure. And across all of these technologies, the unifying theme is responsibility. Civil 3D, GPS, drones, BIMs, machine control. These are all powerful tools, but none of them relieve the surveyor or appropriate professional of their liability. And our board rules are clear. The licensed surveyor is ultimately responsible for the accuracy and clarity of survey deliverables. That means verifying GPS points against control, tying drone photogrammetry to known benchmarks, and ensuring civil 3D models align with approved plans, and checking that BIM and GIS integrations remain consistent. Technology can accelerate our workflows. It can be an amazing option. However, it will never replace our professional judgment. As we bring together alignments, profiles, construction staking, and advanced technology, we need to pause and remember a fundamental truth. Surveyors in Texas are bound not only by professional ethics, but also by the rules of the Texas Board of Professional Engineers and Land Surveyors, commonly known as the board. And every deliverable we create is not just a drawing or a data set. It is a professional statement that we have verified accuracy, exercised judgment, and complied with our state laws. In construction surveying, quality assurance and quality control are not optional add-ons. They are essential to protecting the integrity of both the project and the profession and the public. QA/QC means checking that every alignment ties into the correct control, that every profile reflects verified elevations, and that every label communicates clearly, and every staking plan is internally consistent, and that these reviews, they can catch our errors before they reach the field. Errors that can cost thousands of dollars, delay schedules, or endanger worker and public safety. Think back to Lecture 6, where we discussed the importance of benchmarks and datums in our site surveys. If a surface is tied to the wrong datum, every elevation derived from it will be wrong. Construction, that translates directly to misplaced grades and failed infrastructure. QA/QC is the surveyor's safeguard against these risks. So, unlike many professionals in the AEC industry, surveyors carry legal liability for the accuracy of their work. If a road is staked outside of its right-of-way, or if a drainage system fails because elevations were misrepresented, the surveyor's certification comes under scrutiny. Courts in Texas have consistently recognized that the surveyor's responsibility is not diluted by resilience or by reliance on technology or delegation to others. That seal represents personal accountability. And this is why construction surveying demands a mindset of diligence. GPS, drones, civil 3D models, machine control systems. Again, all very powerful and useful tools that make a lot of our jobs easier. But if they are used improperly, the liability still rests with the surveyor. If we want to use this technology, it is our responsibility to understand it completely, fully, understand not just which buttons to click, but what processes are happening, why they're happening, and why it's important to us. It's why it matters. The board also makes it clear that no matter how your work is performed, that licensed professional must oversee, review, and take responsibility for the final product. The board rules reinforce three core obligations. Competence. The surveyor must only perform services that are competent to perform, which includes understanding the limits of technology, like GPS or drones. Accuracy. Our deliverables must meet or exceed the minimum standards for surveying, whether that means closure on a boundary or precision in a construction stakeout. And lastly, accountability. The surveyor's seal is not decorative. It's not a reason to just be paid more money. It certifies that the work is correct to the best of their knowledge and skill, and that it has been reviewed for completeness. And these standards exist to protect the public. Every construction survey is a matter of public safety, whether it involves placing a stake for a roadway, setting grades for drainage, or verifying as-built utilities. We can summarize the stakes in simple terms. A mistake in construction surveying is not just a drafting error. It's a built error. Once concrete is poured or earthwork is cut, mistakes become expensive and difficult to correct. And more importantly, they can create lasting problems. A roadway with an improper slope, a utility that doesn't drain, or a structure outside of its legal footprint. The surveyor's duty, enforced by the board, is to prevent these outcomes before they happen. One of the most important professional relationships in construction projects is the partnership between the engineer and the surveyor. Their responsibilities are distinct, but their work overlaps constantly, and the success of any project is going to depend on that collaboration. See, the engineer is responsible for the design. They determine roadway widths, slopes, drainage structures, material specifications, and performance standards. Their seal certifies that the design is safe, functional, and compliant with regulations. The surveyor is responsible for measurement, position, and the transfer of that design to the ground. The surveyor ensures that the boundary is correct, the control is accurate, and that the design intent can be faithfully staked and verified. In Texas, the board makes it very clear. Surveyors may not practice engineering, and engineers most certainly may not certify surveys. So why, if surveyors are not engineers, should you as a future licensed surveyor learn how to create designs in Civil 3D? Alignments, corridors, profiles, and even pipe networks, if we can get to that. The answer is that a broader skill set makes you a stronger professional. First, by learning how engineering design tools function, you gain insight into how your deliverables are used by others. When you prepare a site survey or a construction stakeout, the engineer will often take that work and turn it into alignments, corridors, and grading models. If you understand their process, you can prepare your data in ways that fit seamlessly into their workflows. That makes you not only more valuable to your employer, but also a more reliable partner to the engineer. Second, there will be times in your career when you're asked to draft, model, or visualize proposed improvements. Even though you're not sealing the design, your ability to create a corridor model, set up a profile, or generate pipe networks in Civil 3D allows you to provide meaningful support to engineers and planners. And this versatility increases your employability. It allows you to move fluidly between surveying, drafting, and design environments. And third, these skills sharpen your perspective as a surveyor. When you understand the design process, you'll be better equipped to catch errors or conflicts early. You'll see where an alignment might extend beyond right-of-way, where a profile does not tie correctly into a benchmark. By anticipating how designs are created and used, you strengthen the quality of your surveying practice. And this overlap between engineering and surveying is also reflected in the integration of GIS. While not strictly necessary on every construction project, GIS provides the broader framework in which both professions operate. Engineers may use GIS to assess floodplains, utilities, and zoning. Surveyors can contribute by integrating their precise control and as-built data into those systems. The result is a more complete picture of how the site fits within its larger environment. GIS also highlights the value of surveyors who understand design. And a surveyor who can prepare data in formats usable by GIS managers, engineers, and planners adds long-term value to every project, ensuring that the survey work lives on as part of the geospatial record. Ultimately, learning Civil 3D design tools does not mean you are crossing into the engineering practice. It means you're building a broader vision of your own profession. You're not only a technician collecting data, but a professional who understands how that data becomes design, how design becomes construction, and how construction becomes part of the permanent geospatial record. This holistic understanding is what separates a technician from a professional surveyor, and why these skills will serve you throughout your career. As we begin to conclude this lecture, it's important to recognize where construction surveying fits into the broader framework of professional surveying and your future licensure. We spent time talking about alignments, profiles, vertical curves, benchmarks, and responsibilities of staking the field. And these are not just academic exercises. These are skills that will carry directly into both your professional practice and your fundamentals of surveying exam. Construction surveying is the bridge between the foundational work of site and boundary surveys and the highly detailed work of a land title survey, or an ALTA survey. In ALTA surveys, which we will study in Lecture 8, the surveyor must bring together boundary retracement, site condition mapping, and detailed documentation of improvements. Much of that work relies on the precision and workflow discipline that construction surveying teaches. If you can control a site well enough to stake alignments and profiles, you will have the skill set to document improvements and tie them back to property lines in an ALTA deliverable. Think of it this way. Your boundary surveys establish ownership. Your site surveys capture existing conditions. Construction surveys bring the design into the field. Your ALTA survey integrates all three into a comprehensive legal and spatial record. Each step builds upon the last, and construction surveying is the critical transition point between measuring the land and documenting how the land has been developed. The FS exam will also test you on the very concepts we practiced here. Expect to see problems involving vertical curves, where you may need to calculate elevations and points along a curve, determine curve length for stopping site distance, or check grade breaks. Profiles and cross sections, which may require you to interpret existing ground versus design grades, or calculate earthwork volumes from cut and fill. Construction staking, which includes your offset calculations, alignment stationing, and translations of coordinates to the field layout, or even be quizzed on control and datums, ensuring that your work is tied to an appropriate vertical and horizontal coordinate system. Even if you plan to specialize in boundary work, these questions will still appear on the FS exam because they reflect the breadth of professional surveying practice. The exam, which is designed to test not only your specialized personal interests, but your competency across the entire scope of our field. So as future licensed surveyors, you may not always be the one designing a roadway alignment or drafting a utility profile. That is the engineer's responsibility. But by understanding these tools and being able to use them in Civil 3D, you make yourself a stronger survey professional. You can communicate clearly with engineers. You can anticipate where errors may occur, and you can ensure that your surveying deliverables will integrate seamlessly into design workflows. More importantly, this knowledge helps you protect your own seal. If you understand how profiles and vertical curves function, you're better equipped to verify that a design can be staked accurately in the field. If you know how corridors and pipe networks are modeled, you can ensure that your survey data supports rather than hinders these models. So, in Lecture 8, we'll turn to our land title surveys. And these surveys demand a higher level of detail and legal precision than any other type we have studied so far. But the discipline you have gained in site and construction surveying will be directly applicable. You now understand how to capture existing conditions, translate design intent into the field, and maintain accuracy and accountability at every stage. So as you prepare for both your coursework and the FS exam, remember this. Construction surveying is not an isolated topic. It's the training ground for the broader responsibilities of professional surveying, bridging what you measure today into what you certify tomorrow. In this lecture, we explored construction surveying as the bridge between site surveys and the built environment. We saw how alignments, profiles, and vertical curves, while technical in nature, represent much more than lines on a drawing. They are the framework that allows design intent to be carried into the field, guiding contractors with precision and reliability. We also highlighted how benchmarks and control form the skeleton of accuracy, and how GIS, while not always required, extends the impact of survey data into the long-term records relied upon by engineers, planners, and municipalities across the state of Texas. We also examined the critical overlap between engineers and surveyors. While engineers are responsible for the design, surveyors are responsible for translating and verifying that design in the field. For you, as a future licensed land surveyor, learning Civil 3D design tools such as alignments, corridors, and profiles is not about stepping outside of your profession, but about broadening your skill set to anticipate how your work interacts with engineering practices. This knowledge makes you a stronger collaborator, a more effective communicator, and ultimately, a more trusted professional. And finally, we connected these lessons to your path forward. Construction surveying prepares you for both the responsibilities of practice and for the fundamentals of surveying exam, where vertical curves, staking, and profiles will likely appear as core competency questions. It also set the stage for our next lecture on ALTA or NSPS land title surveys, where boundary, site, and construction surveying all converge into one of the most comprehensive survey types you'll encounter. In short, construction surveying is where the discipline of measurement meets the demand of design and law, and mastering it ensures that your work as a surveyor supports not only today's construction, but tomorrow's record of the land itself.